Our next speaker for today, ladies and gentlemen, is Dr. Bangani Ngeleza, who will chair the session on differential privacy, a very current topic in this technological era. And Dr. Chakran cautioned us around these issues earlier on this morning. So I want to introduce Dr. Ngeleza before he introduces his speaker and the session, open up the session for today. Bangani is an organizational development, strategic management, and facilitation specialist with extensive experience working with governments and the development sector locally and internationally. His experience in the South African post-school education training sector includes, amongst others, supporting the repositioning of the National Skills Fund as a center of excellence for monitoring and evaluation. And he's also supporting the ongoing organizational review of the National Skills Fund. He chairs a ministerial panel of experts that advises the Minister of Higher Education, Science and Technology on the quality of SETA sector skills plans, strategic plans, and annual performance plans. His doctoral studies focused on developing a strategic management framework for technology migration to free open source software in the South African public sector. And as an associate of JET Education Services, his role entails planning, monitoring, and evaluation, and the support to the PSET cloud. So with that, Bangani, I hand over to you, and it's such a pleasure working with you.
Thank you. Thank you, Roxana. And good morning, colleagues. Good morning to all of you joining both locally and internationally. And thank you for coming to this session. Let me also start by just extending my best wishes to the people of Ukraine and to Europe in general on the current crisis. Hopefully it gets resolved soon and peacefully. So this session will focus on just getting some insights on a technology that can be applied to publicly share information about data sets whilst withholding information about individuals. The whole issue of privacy, which Dr. Chakran has already alluded to in his input earlier on. And seeing that we're looking at these systems interoperability and the sharing of data, this becomes a very important subject for us to consider. Also, you'll remember that those that are based here in South Africa, the Protection of Personal Information Act came into full applicability towards the end of last year. So it's important that as we speak about interoperability and data sets that can be shared and so on and so forth, we have that in mind. To assist us to do this, I'd like to introduce to you Mr. Nicholas Grislane, who has kindly agreed to come and share with us a technology that they are using for what is referred to as differential privacy. Nicholas is Chief Science Officer at Saras Technologies. He graduated from École Normale Supérieure de Lyon in mathematics and computer science. Excuse my French there. Nicholas started his career in economics and finance modeling at the French Treasury and then at Societe Generale. He co-founded a first company, LFD, in 2012, where he was also leading research and development at LFD. LFD was acquired by Yahoo in 2016. In 2020, he co-founded Saras Technologies with the same founding teams as LFD. Nicholas has a strong taste and experience in AI, data science, technical team management, and entrepreneurship. He is skilled in applied mathematics, software development, DevOps, quantitative finance, and economics. With that, Nicholas, thank you for joining us and looking forward to your presentation. Let me hand over to you.
Hi, thank you for having me. Let me share my screen. So yes, thank you. So today, I wanted to present technical solutions to the problem of sharing data while protecting privacy. I hope I won't be too technical, but I will still try to give a sense and an intuition about the different technologies that we use at Ceres. So first, I will introduce the problem we are trying to solve, which is enabling private data analysis, and I will define and explain what it is. Then I will introduce a piece, a theoretical brick that is essential to, I think, the solution to this problem, a satisfactory solution to this problem. Then I will explain how the basic principle of differential privacy can be leveraged to build complex and state-of-the-art algorithm in data analysis. And then I will sketch how we can compose all this together to build a modern and efficient framework to enable private analysis practically. So let's start with the problem we are trying to solve. The problem is to enable private data analysis. So let's say we have a data set with personal data, so records about a lot of people, but it can be really general data. It can be pictures, it can be text, it can be anything. The important feature of the data set we are considering is that it contains personal data. And we want to compute something about this data. So something maybe analytics, so SQL queries. It can be statistics like linear regressions, logistic regressions, or whatever. It can be advanced machine learning models training, but it can also be modern deep learning on this data set. So we want to compute something on this private data. The problem is that this data may be very sensitive. It can be medical records, it can be education records, it can be financial records. So we don't want to leak any information about individuals. So we want to learn general features about the data, general patterns, but we don't want to risk the privacy of any individual in the data set. So today, the standard solutions are based on removing the less relevant information so that it's hard to identify an individual. It relies on aggregating data enough so that an individual is really lost in a lot of other individuals. It relies on making sure that an individual is spread across several aggregates, and any other heuristics I don't have the time to describe precisely here, but the main problem with most of those approaches are they are manual. They require to understand well what are the privacy risks, so what are the potential attack scenarios. They take time because they are not like automatic. You need to know more or less what data is out there to be used as to attack the privacy of your computation. And most of the time, all those ways of anonymizing a data set, they deteriorate, they alter the data, and so the analysis are not as good as they could be. And to our experience, talking to large banks, this process of anonymizing data can take months because it's manual. It has to be validated by a compliance board. So it's very inefficient. So all this makes private data analysis on personal data very complex today, and it's very inefficient. So here we will expose a better way. What we think is a better way. It's systematic. It's less manual. It's less destructive. It's far more convenient to use, and also it provides arguably a stronger protection. This solution is based on a theoretical framework named differential privacy. So I will introduce the main concept. It's very deep and complex theory, but let me give an idea of what it's all about. So we want to compute something on private data. So we want to run an algorithm on data and get some results. What is differential privacy? Let me introduce it formally before I give some intuition. So differential privacy was introduced by Cynthia's work in 2006. The main idea of differential privacy is to bound the difference in results when I run the same algorithm on two datasets differing by one individual. So the formula expresses this constraint. This definition gives a strong theoretical foundation to privacy protection. It means, for maybe those who are familiar with statistics, that no inference is possible about an individual based on the results of the analysis. And an important point is that it does not rely on any assumption about the attacker. So you can apply this methodology without any experts analyzing the possible attacking scenarios. So it's very systematic. And also it quantifies the privacy loss in the process of running an analysis, and enables the definition of what we call a privacy budget. So intuitively, what does that mean? It means that if you take a differentially private algorithm and run it on two datasets differing by one individual, so here there is a missing individual, then what you will get out of these algorithms will be random. I mean, they will be randomized somehow. They will be slightly noisy, and this noise will be such that both results will be statistically indistinguishable. So this noise will be as small as possible, obviously, so that the result of your algorithm is still useful, but it will be there to somehow erase the influence of one individual, which means you will not be able to infer anything based on the result on any individual in the data set. So it provides a very strong protection. So whatever auxiliary or information an attacker can have to try to infer anything, it will never be able to infer anything about any individual in the data set up to some tolerance. In terms of, in statistical terms, it means that the algorithm will output some results with some randomized components. So it will be defined by some distribution of probability. And differential privacy says that if I add or remove an individual, the distributions will not be too different. One important property of differential privacy is that it composes adaptively. So it means that I can run a first differentially private algorithm and get some results, then a second one, and the sequence of all the algorithms, the composed algorithm, is also differentially private, but with a higher privacy loss. So this accumulation of what we call privacy loss, which is the little bit of information that is lost in nature when we publish any results about the data, accumulates, and we can account for this accumulation thanks to the theory of differential privacy. And it gives a sense to what we call privacy budgets. And if you want to protect an individual, if you want to protect a data set, you have to carefully account for privacy loss, and you can bound this privacy loss so that you're sure no one will ever be able to learn anything significant about an individual in the data set. So to wrap up a bit what I just said about differential privacy, the main features of differential privacy are that it's a systematic approach. So you apply the theory, and then you don't have any questions anymore. You don't need an attack model. You don't need expert judgment. So it's very appealing because you can really automate a lot of things. So you can make a data set shareable without any manual intervention. So it scales well. Privacy loss, which is defined by differential privacy, can be quantified and controlled. And you will see that if you take care of this privacy loss carefully, then you can build a powerful tool to share sensitive data sets. And also, differentially private mechanism can be composed, so we can build very complex analysis use case out of basic building blocks. So here I will give you an idea of what are these basic building blocks that we can consider, and how you can build really complex data analysis scenarios out of them. So first, if you want to publish, for example, an average, a statistical average, what differential privacy tells you is that you can compute the average of the ages, for example, in the data set, and then you can add some random components to the average in the form, for example, of a Laplace noise, a Laplace distributed noise. And because Laplace distributed noise has nice mathematical properties, you will get a differentially private estimator of the average. So basically, you compute some average, like average of the ages in your data set. You add some perturbation with the Laplace noise, and it's very easy to prove that whether you add or remove some individual in the data set, it will not make a distinguishable. It will not have a distinguishable impact on the average. So so you can publish the average. No one will be able to infer anything about anyone in the dataset based on this average. So Laplace mechanism is very used in differential privacy mechanisms. But also adding Gaussian noise is more complex, but it's very widespread in statistics. So it's also very used as a differentially private mechanism. So I will not enter into too much detail, but there are like that different basic blocks. And they can be, as we just said before, they can be composed into more advanced algorithms. So here I will just give you an idea of how these basic blocks can be used to build modern machine learning algorithm, for example, and then to virtually do all sorts of analysis, complex analysis on sensitive data. So I will just give you a sense of how an algorithm that is ubiquitous in deep learning, which is stochastic gradient descent, can be adapted with differential privacy. So stochastic gradient descent is about minimizing some loss function. So in deep learning, you have an objective function and you try to minimize it by following the steepest descent, more or less. So here you do, to adapt it as a differentially private algorithm, you just take the same algorithm, but at each step of gradient descent, you add some random noise. So adding this random noise will make individuals in the data set, they will make them lost in the noise. So it will enable to provide formal guarantees that those individuals will not be significant, will not affect significantly the result of the estimation. So you can compose several of those. You can add noise at every step of the gradient descent, and you can accumulate the privacy loss so that in the end you have a limited privacy loss at the convergence of the algorithm. So this gives you an idea. It's very rough idea of how DP stochastic gradient descent works. But my point is that because all modern machine learning and data analysis can more or less be reduced to some gradient descent, a very large spectrum of data analysis algorithm, from analytics, statistics to ML and advanced AI, can be made differentially private. So differential privacy is really quite universal. You can run any kind of complex data analysis, from natural language processing to image recognition to whatever you are interested in. And actually, there are some notable applications in the real world. So for example, in 2020, the US Census Bureau published their statistics with differential privacy guarantees. So they could publish very detailed statistics, and even for some very small cities with a few tens of inhabitants, without compromising the privacy of any of them. And they could give mathematical proof of this protection. But companies such as Google or Apple, they also use differential privacy to prove that some of their data collection are innocuous for the privacy of their users. So now let me try to sketch how to use this framework in practice, and how we use this framework in practice at Cyrus Technologies. So the idea, so we want to enable data analysis on some sensitive data. The basic idea is to proxy any interaction with the data, because any interaction with the data can be used, can leak virtually information about individuals in the data sets. So we stand in between the data, the sensitive data, and the analysts, and we filter any interaction with the data, And so the analyst can submit analysis jobs, they get results, and we guarantee that the results have differential privacy guarantees. And the goal is to, as much as possible, not disrupt the current workflow of the analysts. So let me give you a taxonomy maybe of the tools that are existing as open source today to do differentially private.
Sorry, Nicholas, sorry for this. May I ask you to wrap up if you can?
Yeah, I will wrap up.
This thing will kick us out, otherwise we're running out of time. Thank you.
Okay. So, very briefly, there are. What I wanted to give you an overview of the different open source algorithms, but I will just jump to the maybe conclusion. So a comprehensive framework, what does it look like? It should, so permission and privacy consumption rights should be managed by the data owner. Any complex query should be available. You should be able to run any analysis with your current tools. Privacy consumption should be optimized across queries. Anyone should be able to run analysis, not just trusted users, and one should be able to use his usual tools. So to achieve that, you need a lot of components, and they are not readily available as open source software. So what you need is a UI for the data owner to manage permission. You need an accountant so that you can accumulate privacy loss. You need to proxy interaction with the data so that you can open the dataset to untrusted users. And also, what we do at Cyrus is that you can write a data analysis job in Python with your favorite tools, and we compile it into a differentially private equivalent. So it gives this gives an overview of what are required to have a seamless experience while working on sensitive data. And this is what we build at Cyrus Technologies. So maybe I will jump to the conclusion. So today, Cyrus and other companies are building tools to enable data analysis with privacy guarantees, to have privacy guarantees in an efficient manner. That is to say, without having to wait 6 months to analyze your data and to have data deteriorated by the process. Cyrus is built upon a lot of open source projects, obviously. So Google and Apple publish, and other contributors have published like building blocks of differentially private algorithm, and we build upon those. And we also are contributing to the open source community in differential privacy. So thank you for your attention, and let me know if you have any question about differential privacy.
Thank you, Nicholas, for that very informative presentation and outline of this technology. We don't have much time left now, so I'll just go straight to the few questions that we've received and allow you to respond to them quickly. There's about 4. From James, he says, the notion of differential privacy is good, but we should be careful not to create a black box approach that few people understand. So yes. And then can I?
Yes.
Let me just ask all the questions, and then you can take them all together. Then the second one is from Diana Ngwana. Can the tool be plugged in any HR system? And what skill experience is required to manage the tool? Can the tool be in-house managed or require a consultant to manage it? That's the second one. The third one, again, is from James. Is DP only useful for aggregated computations? We lose any sense of individual track, even if we anonymize. And the last one is from Dr. Moamanda. What are some of the benefits of differential privacy compared to other privacy mechanisms of privacy strategies for big data? And the last one, do you have examples of government that use DP? If you can just take those quickly, Nicholas.
Yeah,
thank you.
I take them quickly. So I think the question about the DP being another black box, hard to understand. So that's a very valid point. And I think that's why there is, it's very important to build those tools based on open source building blocks, because anyone can then, various experts can have a look at what's inside and can validate that it's a right and protective approach. But really, it's hard. I would say that today most web browsers use cryptography, and everyone trusts cryptography, even though it's a black box and very complex. So I think it will be the same with differential privacy. So we will have to trust some experts, but then once enough people trust them, it's okay to use those tools like cryptography. Can Cyrus be plugged in and managed in-house? So Cyrus, yes, it's a software that can be installed on most like cloud infrastructure. Feel free to contact us if you want us to demo our product. What about about the individual tracks and trying to track individual? So so DP by definition will prevent any individual tracking. It's impossible. It's made impossible by the tool, because it's dangerous to be able to track individual. And that's why alternative to differential privacy are usually rather weak, or they require very strong assumptions about what data is out there, what alternative data, what auxiliary data is out there. Really, if you want to protect privacy, it's really not a good idea to try to have access to individual trajectories. What you can do with differential privacy now is to fit very precise and complex model that gives you all the statistical properties of those trajectories. So you can analyze and classify the trajectories of individual as statistical groups more than as individual. So it's possible to analyze tracks, but not have a look at each individual tracks. And then what are the advantages of differential privacy versus alternatives? So I don't know, alternatives I will assume there are anonymization technologies like k-anonymity, for example. So the main advantage of differential privacy is that you don't have to make any assumption what you publish about a data set with private information, which is not the case of other alternative tools. So basically, any systematic tool that preserves privacy will have at some point to use some form of differential privacy.
Thank you. Appreciate it. So the message, colleagues, just to wrap up the session, is that there is a technology, that can be used to share data and to anonymize the data in a way that does not reveal personal information. And in this way, I hear Nicholas is saying you can actually use this to do all kinds of analysis, including SQL analysis, including serious statistical analysis coming out of that, artificial intelligence and all of that. And the final point, to avoid the black box, we should explore open source solutions. And here we do have a policy already that the state has adopted on free open source software. So that's possible. So on that note, let me hand over to you, and thank you, Nicholas, again for making time and really taking us through this. Much appreciated. Let me hand over to you, Ruxana.
Thank you, Bangani. Yeah, it was so interesting. I had to allow a few more extra minutes. My apologies to the next session lead. But thank you both, Bangani and Nicholas. This has been an excellent presentation, albeit quite tech focused, but certainly helped us to understand much better what happens on the back end.